I'm ready. Okay, hello everyone. Welcome to today's talk about the inner workings of ImageStitch. My name is Markus van Almsick. I'm a consultant of Wolfram Research and working on images since roughly 12 years now. Lately, for version 13, I have been implementing ImageStitch, the registration of several images into a panorama. And since this is a kind of a tour de force through the almost entire area of image processing, I thought it makes up a great theme for Twitch Talk. And I'd like to take you along today through all the aspects of image stitching as I encountered them implementing the command ImageStitch. In case you don't know, since version 13, we have ImageStitch. This is the ref page. Basically, you just have images, you plug it into ImageStitch, and it will figure out how these images are connected and then tries to build a big stitched version, like in this case, where you have a lot of images taken in a park. And at the end of the day, you get a stitched image. All right, so much for the cover. But as I have mentioned, I'd like to really go in deep today and just take you on a wild ride through image processing and the science of stitching images. Okay, the term of, or the technical term to register two images is called image registration. And it's one of the big topics, or used to be the biggest topic in image processing besides image segmentation. That is the partition of images depending on foreground, background, and so forth. All right, so what is image registration? Image registration comes in different flavors. But just to give you a very simple idea of what it is, you basically have two images. In this case, I have two images taken from a microscope, well-colored, very nicely stained images. And especially when you work with a microscope, you usually only see a very small aspect of your sample. And that's why you just move the stage of the microscope further and further and retake images, and thereby you get a kind of a mosaic of the entire big image, but you just basically have lots of sub-images. And that's why you try to do image registration, which basically means you take two images to start with, and then you see how these images fit together. Essentially, if I do it now by hand, by overlaying them just like this, and once you think they are nicely registered, you basically, well, in this case, I just let go, and I have now a merged version of these two images. Now, what I've done by hand, of course, I'd like to automate. And so let's dive in and see how this is done. There are different ways to register. Basically, roughly speaking, probably there are more, but roughly speaking, there are three ways to do it. There's sparse registration via image key points. There is dense registration to basically minimize some kind of image distance. And then there is Fourier registration, if you're just interested in translation, that tries to register two images via the Fourier transform. And I quickly, just for completeness, I like to discuss all three versions of registration. The most common one definitely is sparse registration. And the idea is as follows. You don't really try to match or register every pixel with every other pixel in those two images, but you basically try to find what's called key points in an image, points that have a well-defined location, and then you look at the surrounding. You basically investigate these points, and you just, at the end of the day, just try to register or match the points in the two images. These are the key points in image 1. These are all the key points in image 2. And then the task is to find a match such that at least a subset of these points matches a subset in the other region of the image. Now, how do I do that? Well, first of all, I don't want to take all the points into account. I only want to take those points into account that have a corresponding point on the other side, on the other image. And this correspondence is evaluated by looking at the surrounding of an image, the surrounding of a key point. and you do basically some basic image statistics on the surrounding pixels. And if the statistics of a point here and of a point here match, then these 2 points are considered corresponding points in those 2 images. And so that you don't have to go into detail how this matching is done, there's a command in Mathematica for quite some time now. It's called image corresponding points. And basically what it does, it takes 1, 2, or more different types of key points, image key points. In this case, we take the root SIFT key points, fairly well-tuned modern image key point. And then we look what key points on one image 1, match the key point in image 2, under the assumption that only translation is permitted in this case. So we're just looking at a subclass of all possible transformations, just at translations, because if you move the stage of a microscope, you usually can only translate that stage. You can't rotate it, you can't tilt it, and so forth. So if I do that, then I get now just a subset of points. In one image, I just get here the subsets on one side of the image. In the other image, I just get a subset of corresponding points on the left side. And so what's next to be done is to match this set of points with this set of points. And this is done by a command in Mathematica called find geometric transform, which basically takes 2 point sets and then tries to find transformation of a certain transformation class, in this case translation, to match the points point set 2 to the point set 1, and as a result I get a fractional linear transformation. On top of it, I also get here an error estimate that tells me how much those points deviate from the ideal transformation that I get here. So essentially, it's a fit with the Ransack routine in there to find the best median kind of transformation. Okay, once I have the transformation and the second image, I can transform the second image onto the first image, which I do here. And then I can try to create a larger canvas and plot the entire image. I could have done all of this, by the way, by a fairly old command, which we have for quite some time now, image align. Image align does all the steps that I just explained and takes image 2 and projects it on image 1. Now, in order to have a bigger canvas, I'm just looking at the border points of the transformed image and see what's basically missing. And then I pad the missing parts to image 1 and image 2 and superimpose those 2 images. And that way I get a stitched version of the 2 incoming images, just as if I had done that by hand a minute ago. All right, so a long story for, in this case, still a fairly simple routine. You find key points, you see what key points correspond to key points in the other image. Then for those corresponding key points, you look up, you try to find the corresponding perspective transformation, or just a translation in this particular case, and then you transform one image and the other image onto a common canvas. And all of that now, as you can imagine, is facilitated by the command ImageStitch, which does what I explained just in one go. All right, so this was still quite simple, but there are all kinds of subtleties that now kick in, which makes the whole endeavor much more interesting. But before I get to that, I quickly, just for completeness sake, like to mention the other types of registration. One is the dense registration, and you can invoke that by image align, just by calling up here the method mean square gradient descent. And what it does, it basically takes, I just take here smaller images, left image and right image. It basically overlaps the 2 images and then calculates an image distance, essentially the Euclidean distance of every pixel pair that you generate by putting one image on top of the other. And that distance you try then to minimize by moving one of the 2 images around. And you try to minimize that via the mean square, via the gradient descent method. And I can do this here and move image 2 onto image 1. Look at the boundaries, and then I can superimpose the 2 and get the result. Now this only works, and that's why I have done here just some smaller patches of the two images we just had, on images that have a fairly good overlap. So it is not a method of choice when you have images that just basically have an overlap at, pretty close to the image boundary, because boundary effects would kick in and make this routine useless. So in a way, dense registration is good if you already have a good overlap between two images, and for the fine-tuning part, dense registration is the way to go. It has another benefit, which I quickly like to mention, and that is that it is also applicable to two images that are of different modality. You talk of different modalities in image processing. If one image is, let's say, CT, computer tomography of brain tissue, so basically just trying to render the density of the tissue, and the other one is obtained via a different method. In this case, it's a PET scan, so positron emission tomography, which basically mimics or shows the areas of tissues that have accumulated a radioactive substance that emits positrons, which are then captured and visualized. But of course, tissue that has enriched, that is enriched or has accumulated this radioactive isotope doesn't have to be a dense tissue. So what you see here as an image doesn't have to have correlation with the image here on the left-hand side. However, you can come up with image distances that are independent of correlation, that just look, for example, at the mutual information. So if you look at the mutual entropy as a distant measure between those two images, you can still do a dense registration by basically putting this image on top of this one and just moving it around. And as soon as the common histogram that you can form by these pixels and these pixels, if the common histogram ends up to have a high entropy, which basically means they have a good overlap, then you know that you basically registered. And here I'll just basically show how this is done. If you were to, oops, did I not? Okay, now it's running. Evaluate these images. Okay, so if you were to, for example, put this image on the on the left-hand side, and then just move it in the X direction, you would see how this mutual entropy keeps going down until you are at a certain position, and then it keeps going up. So here, essentially, you would assume to have the best registration, and I can mimic that by basically superimposing the PET scan with a certain translucence onto the CT scan, positioned at the position minus 0.1, and of course you have to start from the center. And then you have an overlay here, and you basically can utilize the information of both scans, the CT scan and the PET scan at the same time, to see where the tissues are that have accumulated the substance. Okay, so that's the benefit of dense registration over sparse registration. As a side remark, of course, dense registration is far more strenuous for your computer to calculate, so it would take more time, and that's why sparse registration is usually faster and preferred. All right, then just for completeness sake, I'd just quickly like to also mention Fourier registration. Fourier registration essentially utilizes the following idea. Let's assume I basically take here a line from the microscopy images that I just had, and assume I just look at the grayscale. Then the cross-section of grayscale values at this line would amount to something like this here. Now, if I move, if I were to take the Fourier transformation of this cross-section, I would get a spectrum of Fourier coefficient that looks somewhat like this here. So I have in Mathematica taken the Fourier transform of this sequence. I only took the first 32 coefficients into account just for visibility purposes. It doesn't help me to put all, 360 coefficients down here. And I'm just looking at the absolute value of these coefficients. I see the spectrum of this cross-section. Now, the interesting effect or known property of the Fourier is that when you move an image, I have to go back one step. I forgot one vital information. What one easily overlooks here, though, is that the Fourier coefficients are usually complex numbers. So these are just the absolute values. But if you plot the imaginary part of the Fourier and the real part of the Fourier, you see that you have all kinds of complex values essentially. And what you have here is that the absolute value of the Fourier is the strength of the amplitude for that frequency, and the complex phase, the mix between real and imaginary part, is essentially the phase of that particular wave that you have to take into account. So long story short, if you have a cross-section of function in 1D, you can convert it into a Fourier transformation, into a Fourier transform, and then you obtain a list of complex coefficients for the different wavelength of that Fourier transformation. And now I basically plot both of these things at the same time. Essentially what I have here, let me just hold this for a second, is a cross-section of the image. And here, basically, I have this Fourier spectrum. Along this line, I have the different frequencies, so zero frequency, so no up and down, but just a flat constant term. The DCT term is here on the left, then one wavelength in the image, two waves, and so forth, going all the way to the right-hand side. And here I have the complex, the real values and the complex values in this direction. And the interesting thing is that if you move an image, in this case, a cross-section left and right, you can have a look at the behavior, how the coefficients behave. And yeah, what you will see is that the coefficient that is for stands for zero frequency stays still. It doesn't change, because essentially what this encodes is the overall offset or the average of the signal. And of course, the average doesn't change as you move an image. But all the other frequencies, they start to rotate, which basically means that you change the phase of an amplitude in a Fourier transformation when you translate the data. And the higher the frequency, the faster the rotation, the phase rotation is as you move along. So if I now again start to move this the cross-section sideways, notice that the rotation essentially of frequencies starts to increase as you go down the frequency axis. Okay, so what does that entail? Basically, that entails if I have two images, essentially with the same function, that are just shifted with respect to each other, they should have the same spectrum of coefficients, and only the phase, the complex phase for every amplitude should be different. And by just basically looking at the difference in phases and then, well, taking into account that the phase shift is once, twice, three times the frequency and so forth, is there, you can basically read out of those coefficients the amount of shift that you have to take to get from one image to the next. And that's exactly what the Fourier method does when you do registration. You basically do a Fourier transformation on the image. You compare the Fourier the Fourier transform of image 1 and image 2, read out the difference in phase, and that phase then tells you by how far you have to move your one image in X and Y direction to get a perfect registration. So I can run this, and now under the hood, it has done the same thing with the Fourier method. And the Fourier method, especially if you just look at translations only, is very fast, and particularly for microscopy images, the method of choice. Okay, so this was the case when you just have two images that essentially have been moved around on the plane, and you just observe translations. Or to a certain degree, Fourier also works if you look into rotations, but I'll leave that aside today. Okay, the whole thing becomes far more intriguing and complicated if you're looking at images that were taken in the wild, basically meaning take images that are not taken from a two-dimensional stage, essentially, but images that were taken in the 3D space. And all kinds of unpleasant things can happen there that make your life less pleasant. Okay, so just to make the point, I just downloaded here 3D geometry from our example database for 3D shapes. And since Wolfram Research is located in Illinois, where you have to love the drive of campus, corn, and cow, I have chosen a cow, since this is the animal you'll see most likely in the center of Illinois. Okay, so let's say I'm having a look at a cow. Cow number one is just basically taking the cow object out of this data. And cow number two is just basically translated via the depth direction by 2 units into the background. And here I just have chosen a viewpoint, and I clearly see 2 cows now, no big deal. Now let's assume I take a second image, but moving from, but I move my or change my viewpoint, the point from which I have taken the shot. Here I was basically looking more at the behind of those 2 animals. Here I'm looking at the front. And okay, now the question is, I have 2 images. Can I stitch them? And the clear answer here is no. Why not? Because essentially what kicks in is the parallax. And basically you see objects from a different viewpoint and different sides of the object. First of all, here you don't see the front of the face. Here you see the front of the cow. So I have here points in this image that I don't have corresponding here on this sense, on this side. Problem number 1. Problem number 2 is that object in the foreground shift far less than object in the background, or the other way around. Usually objects in the foreground shift much more than objects in the background. Depending on how you take the frame of the image, then that may look different. But in general, as you move your viewpoint, things closer to you change more in an image, the image position, as the ones further back. Imagine you're moving around on Earth and you're looking at the moon. The moon doesn't move one little bit, but the trees in the foreground, they will definitely change as you drive by, for example. So that's what you call the parallax, the fact that things in the foreground change more than things in the background. And that's something that changes the entire image, which basically means that this image, there's no way to find a perspective transformation that brings this image onto this image. Absolutely impossible. So I just make this point here because ImageStitch is the art of not taking this case into account. There are other ways when you basically want to derive a 3D scene where you can cope with these kind of scenarios, but ImageStitch and today's talk is not about that scenario. Instead, we are just basically failing here. As you can see, if I take these 2 images, ImageStitch will say the images do not share enough common features to achieve a registration. Basically, it gives up. All right, so what does work? Well, everything is peachy and fine if you do not change your position, but all you do is change your gaze direction, so the direction where you look. That's what you can change. And if you keep your position, then you're fine, because essentially that way, if you rotate the camera, everything stays in the same relation to each other as before. It's essentially just the viewing window that changes. And here I've just imitated such a scenario. So I'm just looking at the rear of the cows, here I'm looking at the front of the cows. And if I now go in for ImageStitch, I should be okay. And you can see, yep, that works. All right, so big message here. If you just take images in the wild of 3D objects, you have to keep the viewpoint fixed. As soon as you start changing the viewpoint, ImageStitch will fail. Now, how critical is that? Well, it's all a matter of relation. So, of course, if you take, let's say, a mountain range and you move 1 meter from left to right, then that 1 meter is negligible in relation to the size and distance of the mountains you're looking at. But of course, if you're taking a picture of a flea that's just half an inch in front of your camera and you move just 1 tiny bit to the left or right, you screw up. So in relation to your scenery, you have to stay fixed. Okay, so just as an example here, ImageStitch, This were images I had taken in a park nearby. And if I call up ImageStitch, the function here, I'll explain how that works, we'll try to figure out what image overlaps with what other image. So it's not just a one-by-one image registration problem, but a one-to-many registration problem. And eventually we'll take all the images and project them onto a common canvas, usually a canvas plane that mimics the plane of the center image. All right, so that's one scenario how ImageStitch works, or what ImageStitch can achieve. There's one more scenario, and that is basically stitching 2D images that you have taken in 3D space. So let's assume you are wandering through an exhibition, and there is this image of a mandrill on the wall, and you try to take a picture up front, and you'll see that if you take it right in front of the it may be very big, you can't back off far enough, so you may not get the entire image into view. It could be the case that essentially you basically have to far too close, and you can only basically get the bottom or the center or whatever into view. But there may be also just the case that if you're right in front of it, you get a glare due to the flash, let's say. In that case, you can move a little bit to the right or left, and you can take basically a picture of that image from the left. You can turn it the other way, whatever way you like. Since all the image data you're looking at is on a plane, you are not screwed in this case, but you can still recover with ImageStitch. And I'll just like to give you an example. Let's say this is one image you took. So basically you were focusing more on the top right corner. The left bottom corner is cut out. And then maybe you have taken a second image where you basically have come in from a tilting angle, and here part of the right-hand side of the images are missing. So let's assume I go in with these two images, image 1 and image 2, and plug that into ImageStitch. You should do fine, and you get an entire image. Why is that so? Simply because there is one fixed depth, and it's all on a plane, and that's why the relation between these two images is still a perspective transformation. And if that's so, ImageStitch can get those two images into relation. So which means that anything that turns out to be an image of image data that pretty much lives on a plane, now be it a painting, or let's say be it the surface of the Earth, which is roughly flat if you don't take the curvature of the Earth into account. Like this image that I took out of a plane, definitely not at the same location as the plane has been flying forward. Even this still works in ImageStitch and can be brought together, because essentially the surface of the Earth has the same function as the canvas of the image that I just was playing with. All right, I wasn't paying attention on the questions that pop up or not. Question, is rotation of the mean always to the right? That is a question I do not understand. So if Zach could rephrase that, maybe I'll get back to it later. Okay, so we now know the scenarios in which ImageStitch will work. One scenario is you don't change the viewpoint. The second scenario is your image data that you see in the image lives on a plane. All right, so what kind of spatial transformation can I consider between two sub-images in an ImageStitch? Well, we have already heard about two of them. One was just translation, like what you have when you look at, let's say, microscopy images that were just obtained by moving the stage of the microscope. There you definitely know that the sample didn't rotate, it didn't back off, it didn't change the tilt towards the microscope itself. So here we can rest assured that we're just looking at translations, and knowing that has a benefit that the search the search space of possible parameters is rather small, usually just 2 shift parameters, and therefore registration would work faster. Let's say, for whatever reason, you're looking at objects that are shifting around on a plane and may also rotate, then you would have to consider rigid transformations that not only take translation, but also rotation into account. If you also back off or zoom into something, so basically if you rescale the image, if you enlarge or shrink objects, then the transformations at hand are similarity transformations. If you also skew things, then we're looking at affine transformations, and the most popular one, of course, is perspective transformation, which are described mathematically by linear fractional transformations. A quick side remark is that when you just pick up a panorama by rotating the camera, you are living in this transformation class, a perspective transformation class. But strictly speaking, the possible transformations you're looking at, just the rotations of the camera, is a subgroup, so a subset of all possible linear fractional transformations. But we do not have a dedicated class for that because it's a little tedious to implement. And usually one is fine by just looking for the perspective transformation, and usually it is just then the transformation that mimics the rotation of a camera. All right. Now, what we haven't talked about yet is the common canvas that we want to end up on. Obviously, when we have 2 images, those 2 images do not naturally live on the same canvas or on the same photo sheet. And if we stitch them, we essentially have to define one common canvas. And if you just play it simple, and this holds true for the first version of ImageStitch, you would go and say, okay, instead of having 2 planar canvases that I have for image 1 and image 2, I have to choose another common canvas, another plane, and have to project everything onto that plane. Essentially, that is also just a projective transformation of this image to the plane and that image to the plane. And there's no difficulty in that. There are other issues coming about because of this. So if I have here just for the geometry, if I have these 2 images and one is pointing this direction, the other one is pointing this direction, or has been taken in that direction or the other direction, then I have this kind of common projection. However, what happens if the direction of a camera of one incoming image is starting to deviate quite a lot from the direction that the common canvas is set up? Well, then these things happen. Let's say I rotate the canvas. You see that images that have a large angle between the normal of this common canvas and the viewing direction of the sub-image, they start to get skewed quite a bit. And this is just, I think, an angle of roughly 45 degrees. You can imagine that as soon as you get close to 90 degrees, the projection of this image onto the common canvas gets skewed more and more and gets larger more and more. And the same holds true if you start to tilt the whole thing, then the same thing can happen. And the same holds true for the other one. Okay, so nasty side effect. First of all, the canvas that you have to have in order to capture the entire image needs to get bigger and bigger the larger the mutual angle is between the angle of the canvas and the angle of the incoming image. Secondly, the larger the canvas and the larger the transformation, the longer it takes your computer, and Mathematica in particular, to create such a stitch. And if you ever encountered the case that sometimes your machine may crash or basically seem to get stuck, then that was most likely the case that the incoming images that you had basically had a wide spread of angles. And the wider the spread of angles, the larger the resulting canvas has to be if it's a planar object. And the more tedious or the more effort you have to take in order to project or transform images onto this large canvas, leave alone that the resulting image may get bigger and bigger and basically exceed the memory capacities of your computer. So, long story short, the problem is that this only works for incoming images that have, let's say, a spread of angles of up to 90 degrees, so not of up to 180 degrees, that would essentially end up in an infinitely large resulting image. All right, so how do we counteract this kind of scenario? Well, we just change the canvas geometry. And the next best choice, instead of having just a planar, is a cylinder. Well, why a cylinder? First of all, it already covers, at least in one plane, all directions. So no matter what kind of images come in, you can just rotate the coordinates of the resulting cylinder, and actually it won't matter any at all. It's just basically that the image frame may shift by doing so. What still does have an effect is if you tilt the angle of the cylinder axis forth or back, you have the same skewing angle that you have with a planar canvas. But nevertheless, especially for an angular spread around, let's say, the horizontal plane, this is the geometry of choice. And that's why now in version 13.2, ImageStitch will also support this kind of canvas geometry. Then the next best thing, of course, would be to just basically have a spherical canvas geometry, because in this case, no matter where you orient your camera, you will always have a proper finite sorry, I shouldn't move this, finite canvas area in this scenario. The only drawback, why this is not really done internally, there's a trick to it, is that now the canvas geometry has an intrinsic curvature. So strictly speaking, you cannot roll out your image that you project onto this canvas, pretty much like you cannot roll out the surface of the Earth onto a map. You will have to have some kind of mapping, essentially, at the end of the day, to make sure that the resulting image is still an image in a plane, in some kind of plane, in order to cope with this. And well, that's exactly what's being done. At the end of the day, you basically project your images on a sphere, but at the end of the day, what you get out of ImageStitch essentially is a kind of a world map of that projection by basically taking the surface here, cutting it open, and then projecting everything back onto a cylinder. But it's not exactly the cylinder projection we have here, because this goes to infinity. If I look further up north, sorry, I should tilt it this way. You see here we have these images that get very big. That won't be the case because you have a kind of a Mercator projection here in this spherical scenario. All right, so this is a way to improve your ImageStitch, and we'll get to that in a second. Okay, now I will talk about all the other things that can go wrong. And the next thing that can go wrong, besides not finding the proper spatial transformation between two images, is also the color transformation that you can have between images. And for that purpose, I will take this example, 4 shots that I've taken out of my office here in Germany. And what you see here is just basically crane. And so basically I took an image of the street and also an image towards the sky in the background. The background was basically sky, just a crane. And what happens in these cases is that the aperture of your camera will change. And that means that the whole coloring or brightness of this image is intrinsically different than in this image. And you can nicely see that by just basically doing a simple image align of image 2 and 3, and then superimposing that on image 2. And you can clearly see that where this image was taken, the aperture was much smaller, and the image essentially appears to be darker than the image that was taken down here, which is essentially image 2. So what does it tell us? Not only do we have to make sure that images are aligned geometrically or spatially, they also have to be aligned or at least equilibrated to a certain degree with respect to their color space. And this is done via what's called histogram equalization or histogram transformation. And I quickly like to give an old example that we had in Mathematica for quite some time. And that is, let's say we have two images, like here, the image of the church in Auvergne in France. And here, essentially, not an image, but a painting by Van Gogh with quite a different color set than what you see here in the natural image. So assume that basically you have these two images here in the overlapping region. One has one histogram and the other one has a different histogram. So if I were to plot these histograms, first evaluate those, then I see here, this is a histogram of the photograph. Unfortunately, it has quite some saturation in the blue channel. And here I have the painting by Van Gogh, which has a much nicer, warmer kind of distribution of colors. Okay, and what one does now is by squeezing or thinning the density of the color space here, I can try to come up with a transformation that takes this histogram and ends up in this histogram. It's same as converting basically distributions. One distribution set to the next distribution set, you basically just tweak the density of your domain, and thereby you can create a transformation that takes this histogram into this histogram. And if I do this in Mathematica, I call up histogram transform, and essentially now you see the photograph in the color palette roughly as Van Gogh was seeing it almost 100 years ago, or more than 100 years ago. All right, so, and what does it mean? At the end of the day, it basically means that this new image has roughly the same color distribution as the one you have here. Okay, so that is what needs to be done in the overlapping area of this darker image and the brighter image. And if you do so, then you get what ImageStitch does for you under the hood. Basically takes those images up there and puts everything into one image, and you basically can't see any difference anymore. The transitions are properly done. Okay, looking at the questions. If I take photos of an object all around it, can I construct a 3D modeler for it? Or does it require an entire different technique? It requires a completely different technique. I'm looking into these techniques. It's far more laborious to generate a 3D model of an object than to create a stitched image. And it's beyond of today's talk. There are examples, for example, for stereo vision on our marketing pages on the web, where you can see how to reconstruct, let's say, a face if it was taken from 3 different angles. But in general, we do not yet have the capability in Mathematica to generate 3D models when an object has been imaged from different viewing angles. But it's definitely something on our to-do list. And there are really nice examples. Or the most cutting edge technique nowadays is called NURFs, so neural radiant field. Basically, same spelling as those obnoxious guns my son is always playing around with. So if you look under NERF, N-E-R-F on the web, you will see a very nice neural network approach to reconstruct 3D objects when viewed from different angles. Something to come in Mathematica, but it's not there yet. Okay, having said that, this concludes roughly the outline that you have to equilibrate not just the spatial geometry, but also the color space when you do stitching. Okay, now I just basically like to point out that there are all kinds of additional difficulties when you work with more than 2 images, because as soon as you have 2 images, it's clear what image to adjust to what other image. In reality, if we have a whole bag of images, like in the scenario of the park images, under the hood, we construct a graph, a network, that basically denotes as its vertices all the images in the data set, and then as links, all the overlapping transformations that have been found between these images. So you can see that this image has an overlapping area with this image, but none with this. So essentially, there is a link from here to here, from here to here, but not a link that goes all the way from the left to this point. So basically, doing a registration among all the images at hand, Mathematica under the hood creates this kind of graph, and then, first of all, tries to figure out what is the center image, and then from that center image constructs the best or the shortest, whatever the shortest is in this case, path from that center image to every other image, so that one has a mutual transformation among all the images. And from that, we can then basically deduce a common projection onto a common plane. And I just bring this up because here you can see that it is really helpful to have a pretty comprehensive system as Mathematica, because we have all the graph routines built in, so I can readily utilize them to work in ImageStitch as well. Okay, once we have everything in place and start to project images onto a common canvas, the issue is that sometimes the matches are not super perfect, because you may have moved your position, or the optics of the camera are not linear, have nonlinearities, or essentially the key points have not been matched properly. And there it's always helpful, but even if you have a perfect match, it's always helpful to blend two images. And instead of doing that now, in particular for the images at hand, for two images in the ImageStitch examples, I do this now for two portraits, because here you can visualize it much better, because these two portraits or images are quite different, so you can see the effect of blending much better. Being a physicist, I have taken the images of two physicists, Werner Heisenberg and Erwin Schrödinger. And since they basically both invented, to a certain degree, quantum mechanics, one via matrix formalism and the other one via wave equations, they basically found the same thing, or the two sides of the same medal. So I'd like to merge their two faces. And one simple or straightforward way to do it would be to just cut one half of the image here, take it away, cut the opposite half away on this image, and then just put them together by assembling them. And then you get something like this. Okay, what you instantly see here is that if there's a transition that amounts to an edge, your visual system is very sensitive to these kind of changes, and you instantly see this dividing line that basically partitions the left and the right image. And that's something, of course, we don't want to have in our stitched images. These transitions should be smooth. And there are essentially two approaches, one already implemented in Mathematica, the other one is soon to come. The one implemented is called feathering. And the feathering is a very straightforward method. The idea is that you basically create a smooth transition, a kind of a blurred transition from one image to the next. And there's a very simple way to obtain that in Mathematica, and that is create an alpha channel, or an alpha channel essentially, and create one with a smooth transition, and then apply that alpha channel to one image, and then superimpose that image on top of the other image. And then you have this feathered transition, and you see that these smooth edges are much harder for the human brain to pick up, and therefore this looks much better, much more coherent than the previous image. So that's something we automatically do currently in ImageStitch. Essentially, there's a hard border being calculated between images, always halfway between image centers, and at that boundary, we basically apply feathering. Another, a little bit more mundane way to do it is to do multi-scale image blending. And the idea is very simple. Instead of applying or just concatenating images at one scale, I basically do that at, well, this doesn't help a lot, at all different scales. So what basically I have here is I take an image pyramid of, oh, sorry, now I know what I did, of both gentlemen of Werner and Irwin. And if I now, for example, just take the first one, now just do 1, all. No, sorry. I'm getting there, just a minute. I basically get a Laplace transform of all the images that make up the pyramid. Now, what is a Laplace pyramid? Basically, it is an image that is being downsampled from the next to the next, always by a factor of 2, until you end up essentially with 1 or maybe 8 or 4 pixels. And those pixels you then just leave, and for all the other images you just store the differences between the image that you had down here, which you can enlarge and then add on top of this one, and the difference that you get because of rescaling. So essentially what you do is you take an image, downscale it, and then subtract the upscaled version from the original image, and you get this one. And then you do the next step on this one, this one, this one. So essentially what you do is for every scale or every resolution of an image, you basically just store the edges or the things that change in the image at that scale, and you do that all the way until you end up with a scale that's essentially a pixel. You do that with a left and right image, and then you can just basically take at every level, let's say the left half of Werner, the right half of Schrödinger, Irwin, and plug them back together, and then you reassemble the image pyramid to images, and you get this image as a result. And interestingly, I didn't blur here. I basically made sure that I combined these images at all different scales. And you see that also I didn't blur. The human visual system still comprehends this as a fairly coherent image without any soft transitions. So that's another way. And of course, one could combine even feathering and multi-scale blending, something we will consider in future versions of ImageStitch. All right, and last but not least, now that we know how to create stitched images or panoramas with a whole bag of images, I quickly like to introduce another nice little function that I submitted to the Wolfram function repository. Maybe it's worthwhile to give a quick show of this repository in case you didn't know that yet. If you have functions that don't make it into the system or that may be useful for everybody else, but are not up to a quality yet that makes it into the system, there is the Wolfram function repository. And you can scroll through this here, look at all kinds of different functions, and then you see here functions that just blur background of an image, and that, let's say, take the square of an image, or no, just check if the image dimension is square. There's all kinds of effects. It's great fun browsing through here. Anyway, so just wanted you to be aware of this. I have taken this spherical image function and submitted that to the function repository. But for today's scenario case here, I basically have the implementation readily available. Spherical image basically is the following. It takes an image, which essentially is just like a map of the world, an image, a 360 image of some object, or actually a 360 image of a panorama, so essentially the inside of a sphere, and it will project that image onto the inside of a sphere so that you can basically turn any direction and see what you would see from that vantage point. So the true beauty of this command, by the way, is that it has a fairly refined discretization of the sphere itself. So it gives a pretty good image. And in order to demonstrate this here, I quickly like to upload an image taken by the European Space Observatory, which is located in Chile in South America. And they basically provided this image. So basically, this is an image taken 360 degrees all around next to the observatory in the Andes mountain. And since they have very little atmosphere left, you have a beautiful vision of the stars, the sky at night, and you can see all the stars and even the Milky Way. Now, it would be great to mimic here a 360 sphere around you in order to view this. And you can imagine this to be, let's say, the result of a image stitch that has been projected onto a sphere. So this is spherical image. If I just provide the image itself, it will pop up with essentially a viewer, which is nothing else but a sphere, where in the inside you basically have projected the image above as a texture. And now you can take your mouse and essentially scroll around. And unfortunately, this is a little bit bumpy because I do broadcast with my machine, and that makes the whole experience a little bit more bumpy. If I do not run Zoom, this is an absolutely smooth experience. Okay, so let's look up for a change. Oops, I have to look up, not down. And you should have a look at the Milky Way, for example. All right, so this is a kind of a VR viewer that's upcoming in Mathematica. And well, let's just try to also view the whole thing from the outside quickly. You can say the viewpoint changes to, let's say, 0 -2 -0. And now I don't see the sphere from the inside, but from the outside. And you can rotate the sphere and just see how this image is being stitched onto the sphere as such. So you're not inside that sphere at the center anymore, but you're viewing it from the outside. All right, so how would that amount to, or how is this being done in ImageStitch and the stitching I had done prior? Well, I can do this kind of projection, but actually I want to have a sphere projection. Do it again. And here we go. So this is now essentially the projection that you would get if you were to map the thing onto a sphere. The one thing that is missing, though, is are all the angles that I didn't take pictures of. So what I have to do here quickly is I have to pad the whole thing a little bit. Knowing the focal length of my camera, I can deduce how large the image should have been to go 360. I didn't. Okay, I still have to do it once again because I didn't assign it to a variable. So let's do it again. Okay, yes. So at the end of the day, this is the entire map that I need in order to project onto the sphere. And then I can take it, and here I have my 3D viewer, and basically can look to the right, or to the left, or look to the right, can look up or down. All of that is doable in the viewer now. And same holds true, of course, looking from the outside. Now it's projected onto a sphere, and you can rotate the sphere and maybe take a peek from the other side, as it should have been actually. All right, so this basically concludes my little tour through the difficult patches of ImageStitch. So I hope you now appreciate the functionality that is provided to you via ImageStitch command a bit more, knowing what's being done under the hood. And I hope you enjoyed it, A, and B, please stay tuned, have a look at coming versions, because I'm destined to add more and more to this function capability as it is right now. All right, any questions besides the one that I have here, the 3D object or the 3D reconstruction I answered already. I don't see anything else. So that would leave me with nothing else to talk about. And I'd like to sign off at this point. Thank you. Thanks for joining.